A big part of what we did this year is using the first derivative and the second derivative to define curves and shapes. So on the final, there will definitely be a problem like this, and it will be something not super hard, but it won't be y equals x squared either. It'll be something you have to take the derivatives of and justify. I just took an example problem here, and it says find everything, right? If you read the bold instructions, find the intercepts, find critical points, intervals increase and decrease, intervals concave up, concave down. All right. Every time you do a problem, you should always start with the simple thought of what is my domain. This is a rational function, all right? This is a rational function. It's always all reals, except what makes the bottom 0? I think plus or minus 4 make the bottom 0, right? So I know there are vertical asymptotes at plus or minus 4. At the same time, all right, so maybe right away I even dot those in, right? Those are vertical asymptotes at 4. All right, and then I can look at this and say, well, I know a couple other facts. I also know that this has a horizontal asymptote of y equals 0, right? Because we look at this function, right, and it's x over x squared. What's the limit as x goes to infinity of f of x? It's going to go to 0. Now, what confuses students when I dot this in? I'm going to dot it in right now. What confuses students often about this, all right, if I save this, I'll put it up here, is the other thing I like to do is I like finding the intercepts right away. There is a 0. What makes the numerator 0? 0. So even though it has a horizontal asymptote of 0, guys, around the origin, that doesn't apply, right? So it does go through 0, 0. So there's our graph to start off with, all right? And if we've found the x and y intercepts right here, right? So I could label that, I suppose, x-intercept, y-intercept, and you can do this on my final like that. We have found both the domain, we have found the limit as x goes to infinity, the horizontal and vertical asymptotes. And I would take all of this right there. So now really what I got to do is find critical points, increasing, decreasing, concavity. And then we'll start sketching this thing out. The derivative of this has to be taken. All right? So if I go here and say y prime, 1 times x squared minus 16, I'm doing the quotient rule, right? Minus x times derivative of x squared minus 16 is 2x. All over x squared minus 16 squared. I have to simplify, guys. This is where the simplification comes in. I see x squared minus 16 minus 2x squared. So I see minus x squared minus 16 over x squared minus 16 squared. All right? Ugly, right? It is ugly. Everybody, at this point, be careful. Don't cancel one of these. I probably would do this, but I'd probably leave it like this. You could bring a negative out front, right? But I always leave it like this. Everybody, so I look at this, and I think to myself, what are going to be my critical points of this function, okay? I want to make sure and I look at this, and your first instinct is critical points make the derivative. So I would look for some definition here. And where's y prime equals 0 or undefined? You guys agree? That's the critical points. Everybody, nothing makes the numerator 0. Because if you factor out the numerator, there is no real number that will make the numerator 0. All right? You should be able to kind of almost picture in your head a parabola shifted up 16. It's not going to, there's no number here. Likewise, the denominator, right, has plus or minus 4 making it 0. But what do we know about plus or minus 4? It is not in the domain. So guess what? You guys hate this, but the answer to this is that there are no critical points. Because it really tests your knowledge, and if you don't feel comfortable with it, often you try to force something to happen. It could very well be this on the test, all right? There are no critical points. So what that probably means is this runs to infinity, doesn't have any local max or local mins, right? So the next thing was concavity, all right? So I'm going to take the derivative of that. I'll do it in blue. Y prime prime equals derivative of negative x squared minus 16. I think it's negative 2x. Now, this is where it gets fun, right? Times the bottom minus the top, which is negative x squared minus 16, right? Times the derivative of the bottom, which is 2 times x squared minus 16 times 2x all over x squared minus 16 squared squared, which the last time I checked, squared squared is to the 4th. Again, depending on how much you practice, how little you practice, at this point you are either feeling okay or throwing up in your mouth a little bit, all right? At this point, it is always the same when you have these big rational functions, all right? Usually, you have to see that x squared minus 16 is common before you do anything. There are 3 terms on the board, and x squared minus 16 will cancel out of 1 each. So I can change this 2 to a 1, cancel this completely, and change this 4 to a 3. All right? Algebra time, right? Now it gets a lot easier because there is a lot of work in the numerator still to do. Distributed negative 2x. All right. I see that I have a 4x left. You guys agree over here? So I have to distribute negative 4x to these. All right. And that's still all over the bottom cubed. Now I'm looking for like terms in the numerator. Is it 4x cubed, right? Plus 30x squared plus 64x all over the top bottom. And I'm feeling like, you might, at this point you might be like, why do I care? I can pull out a 2x, right?
Why did you change from 32 to 30?
Oh, I'm sorry. I made a math mistake. Good catch, good catch. Somebody's watching me. Friday afternoon, feels like. How about, oh, this, and listen, I probably had a big problem solving this. Is that right? Does that look better? And math mistakes are killers. Now listen, I wouldn't grade much on math mistakes. All right, so I have a parabola here, all right? And hopefully you see, again, that there is only 1 0 happening here, okay? For this y prime prime, okay? The y prime prime has a 0 at 0, right? What y prime prime equals 0 at, because that 2x is out there. Yeah, that's all I looked at, because I look at the x squared plus 16 plus 32, and I could try to solve that, but does that factor? No, and again, it helps if you're really good at the parabola portion of this, right? If you think of that as a parabola, all right, it's x plus 8, right? It's going to be squared plus 8, so it's going to be minus 64. So there's probably some answers here, all right? I can't think, does it factor? I can't think of any factors here. You guys? Yeah, and find that 0. And listen, on the test, if I'm going to tell you to do it with no calculator, guess what? This is either going to factor to some zeros, right? Or it's not. 32 and 16, right? I can't think of any. 4 and 8? Nope. 16 and 2? Nope. 12 and a fraction? Gosh, I hope not. Right? So we have x equals 0. So everybody, this is a possible point of inflection. Not a guaranteed, right? Because what makes a point of inflection is a change in sign of concavity. Holy cow, we're going entire page so you get a feel for what we've done and why one of these problems will be on its own page. All right? Because I'm going to box all this up, group this all, and make this super tiny. Because I don't particularly care about much of this. You probably need to see the second derivative here. All right? I probably need to see the second derivative for that. But everybody, at this point now, you can make a table. You can make a table. You're your table has x, f of x, f prime, and f prime prime. And I know negative 4, because it's an asymptote, we got to include it there so we know this is undefined. I know 0 from the second derivative, right? And I know positive 4. So all I really care about on the first derivative, because there were no critical points, is what is happening, all right? And I'm looking up here at the first derivative right there. You guys see it? And this, at this point, I probably would do this factor, so I see this. Because my $1 million question to you guys, when you look at this, is there any way, when you look at x squared plus 16, that's always positive, right? No matter what you put in for x. When you look at the denominator, x squared minus 16, quantity squared, is always positive. And then it's always times a negative, so what do we know? We know this is always negative. So this is a decreasing function, all right? Guys, that automatically sets it. That, truth is, that's enough information for us to graph the whole thing right now. All right? Because we know it's decreasing, decreasing, decreasing. Guys, I guarantee that's the curve. I don't need more information than this. And I know that 0 is going to be a point of inflection for concavity, just from one derivative. All right? First derivative says these are the intervals decreasing. Negative infinity, negative 4 is decreasing. Negative 4 to 4 is decreasing. And 4 to infinity is decreasing because they're always negative, all right? Now, I do have a derivative here of, this derivative is 0. And again, if I plug into those problems, I can figure out the sign for the concavity, all right? If I do that in red, and again, I have to use this whole disaster over here, all right? Now, this gets very hard, all right? I'd be more tempted often, all right, to do my work based on the other one. You could plug in a huge number like negative 1 million, negative, negative, or negative positive on the bottom, negative in there. You're going to get that this is, you can tell when you look at it, right? Curve is below the lines, concave down. You can tell that in this section you're going to get concave up, it's going to be positive, concave down, and then concave up. So concave down, and maybe I can do this in one section, goes from negative infinity, negative 4, and from 0 to 4. Concave up goes from negative 4 to 0, and 4 to infinity. Now everybody, what's that mean? That means there is a sign change at 0, 0. So what's the point of inflection? 0, 0 is the point of inflection. And we just did the whole problem. Not too bad. I think on a final, I would be less likely to give you a problem where the second derivative got so ugly. All right? But we got to keep practicing. We should be able to do an easy rational.